Hello, welcome to the Blue Waters webinar series. I'm Scott Lathrop at the National Center for Supercomputing Applications, and it's a pleasure to have you join us today. It's my pleasure to introduce Gerd Heber, application scientist with the HDF group, and he'll be talking about what's new in HDF5 version 1.10. With that, thank you again for joining us, and I'll turn it over to you.
Thanks, Scott. Thanks for having us here at NCSA. Today I would like to tell you a little bit about what's new in HDF 1.10, which is sort of one of the major new releases in the HDF family. Before I do that, I would like to tell you a little bit about the HDF group, who we are and what we typically do. We have been in this space that's now called big data in enterprise, in science, and so forth for about 30 years. In fact, we talked about big data before the term became what it is today. We are a small company of about 40 employees, and we are based here in Champaign, but we also have an office in Boulder, Colorado. And HDF is, of course, HDF5, that is sort of the heart of our open source ecosystem, and it's in use worldwide. And for example, if you do a search on GitHub, how many projects utilize HDF5 in some form or another, you will come up with, last time I checked, 800 plus projects, could be 900 now, I'm not sure. And HDF itself, as many of you might know, is sort of a de facto standard in sort of the science engineering space, but increasingly so also in in the enterprise space and government. What does the HDF group do? We develop products, the HDF5 library as sort of our flagship product, but then we also have things that you may not know about yet. We've developed, for example, connectors like an ODBC driver. We will soon have an announcement about an offering in the cloud, and then add-ons for to be used in conjunction with HDF5 for compression and encryption, for example. And we also offer a variety of support options at different levels, and we also support if you have questions about the use and the effective use of modules like H5Py, PyTables, or Pandas. And of course, we offer training around HDF5. Finally, we also offer consulting, and that can go as far as implementing a new feature for you in HDF5, but also we offer general HPC software engineering in different disciplines, including financial services, but also we offer expert services in areas like metadata and I/O in general. Now, this is not exactly an outline. This is just sort of a mind map of the topics that we will touch on today. We will not be able to exhaust these different topics. But before talking about HDF 1.10, because it is such a major new release, I will spend quite a bit of time to talk about the release cycle, and I hope that will help you understand the impact that it might have, that if you want to switch now to HDF 1.10, or if you begin development now with HDF 1.10, what the implications are in the ecosystem around you, which might include applications like MATLAB or IDL and so forth, and then the compatibility of the file formats, the APIs, and so forth. And I call this HDF5 from release to release, and would like to sort of paint that picture for you of understanding how we version the software, the file format, and so forth, and what the implications and our guarantees, if you wish, for the compatibility between these different versions are. If you look up on Wikipedia, there are basically two kinds of compatibility that are relevant in this space as far as HDF5 is concerned. There is something called forward compatibility, and that is basically the ability of a system or a software to accept input intended for later versions. So, for example, and we will come back to that in a moment, if you create today an HDF5 file with the latest version, HDF 1.10, what are the implications for an application for which you may not have source code that you just have in binary form from another vendor? Will that application be able to read the files that you start creating now with HDF 1.10? So that's that issue of forward compatibility. The other, maybe the more intuitive and more straightforward kind of compatibility is what people commonly refer to as backward compatibility, which when you use the new system to access, in the case of HDF5, files that were written by an older version of the library, if that's possible and how that's possible, and if there are any caveats, what are they? So those are the two types of compatibility we'll be talking about. And before we talk about compatibility, let's talk about versioning, because in a way, this compatibility is sort of conditioned on versioning. The first question is, what gets versioned in HDF5? In the case of HDF5, we version the library or the API and the file format. And I will be more specific about that, because versioning, as we will see in a moment, does not necessarily mean that there is a version number. The reasons why we version the library and the file format are mostly, as with any software and the imperfections that it may have, we fix bugs all the time, and so that requires versioning. We make improvements to performance, and of course we always add new features to the library and then subsequently to the file format if that feature then requires something new in the file format. And that also, as far as the library is concerned, is in some cases means API changes, new APIs appearing, but also modifications to existing APIs. And if you are a programmer, let's say you program in C, then sometimes part of these APIs are certain public structures, for example, and there might be new members in that, or new fields in that structure. Some might go away, the types might change, and so forth. So this is really what gets versioned and some of the reasoning behind it. Now, the typical questions, let's say you are using HDF 1.6, HDF5, 1.6, 1.8, or 1.10 today. Well, if you are at 1.10, then at the moment there is no upgrade path to a newer version, because that is the latest version. However, if you are on 1.6 and 1.8, and you contemplate the upgrade to 1.10, here are some of the questions that we will talk about and that might be on your mind. Well, first of all, we get bug reports all the time, and unfortunately, we do not always have the resources to address them immediately. So some of them sit around for quite some time. So you may have, worst case, submitted a bug report 5 years ago, and now finally we got around to fixing it. And another thing is, will I be able to read my old files with the new library? Another one is, if you have an existing application and let's say we made some performance improvements or other improvements that make you think, well, I'm not going to change my application. However, it would make sense to sort of simplify my my maintenance cycle, and I'm going to link, or at least I will try to attempt to build my existing application without any code changes with the latest version of the HDF5 library. Is that possible, or under what circumstances can that be done? Again, third-party applications like MATLAB, like IDL and so forth, of which you may not have a current version, a version that is maybe 3 years old, will that actually work with HDF5 files? That an application that you have developed recently that uses HDF110, will MATLAB and IDL be able to read those files? And then, of course, most of us don't operate sort of in vacuum or without any interaction with the outside world. Typically, you are part of a community or you work in a large organization and you interact with other people who have other versions of software and so forth. How can we make sure that they are not impacted, they are not affected by decisions you might make about changes, upgrade changes for HDF5. Let's talk about, so we talked about we version the library and we version the file format. Let's talk about library versioning first. Any HDF5 library version is sort of this numerical form HDF5 x.y.z, and sometimes there is a hyphen suffix appended at the end, as very common in software development. X is called the major version, Y is called the minor version, and Z is what we call the release number. And sometimes, mostly for development purposes, testing purposes, the suffix is present to indicate that this is not sort of a production release, but it is a feature branch. It is something that we give to people. Let's say we fix a bug, then typically we go back to the team or to the person that reported the bug and give them a branch where we say, we believe we have addressed that problem. Can you confirm that for us? And so before we roll it into an official public release. And then here are some examples of these version numbers I'm sure you're all very familiar with. Continuing on library versioning, so the release number changes, the Z in that XYZ notation changes pretty frequently. We have at the moment about a 6-month public release cycle, so every 6 months for both 1.8 and 1.10, the Z changes. So for example, in the 1.8 family of releases, the Z is at 19, and in the 110 family of releases, the Z stands at 1. So 110.1 is the current 110 release. If that number changes, there are certain things that we guarantee you that do not happen. Number one is there are no changes to the file format. So within a Y constant family of releases, the Z might change, but at the file level, at the file format, there are no changes whatsoever. There are also no changes to existing APIs. So if you look at I have some links, some URLs for you later where you can look at the C API, for example, or the Fortran API and so forth. Within a change of the Z, the release number, there are no changes to the API, to existing APIs. There are also no changes to public data structures. Again, as a C programmer, there is a certain structure that tells you something about, let's say, the metadata cache configuration. That structure will not change from release number to release number. There might be new APIs, and of course, for them, there will be additional APIs, typically additional function APIs, but there are no changes to existing APIs. And which means that if you're tracking a particular release number sort of where the y stays constant, so let's say a 1.8 family or 1.6 family or the 1.10 family, within that family you should not encounter any problems whatsoever recompiling your application with the newest version, because there are no API changes, there are no file format changes. One more thing, the minor version, and it doesn't do it justice. The minor version changes very frequently, and the importance is actually not minor. The importance is actually major. However, the one which is in a release numbering sense, the major component here, the one has never changed, and it's questionable. We don't know if that number will ever change, but Y changes very infrequently. So if you go back, look through older release notes, how long it took to get from 1.6 to 1.8 and now from 1.8 to 1.10. In some cases, there's almost a decade for in between changes of that Y component of the release version. The file format may change and has changed. So, for example, from 1.8 to 1.10, we have made additions and enhancements to the HDF5 file format, and we'll talk about that in a moment. We've added new APIs, and this is also a situation when we go to a new minor version that old APIs might be removed or deprecated. And we also make changes to public data structures, and which are handled the same way that we handle deprecated APIs. Let's talk for a moment excuse me, about the file format version. The first thing to know is that, yes, there are versions of the file format. However, there is no file format version number where you could say, okay, for example, well, since we know that between 1.8.16 and 1.8.17, 1890, or even 1.8.0 and 1.8.19, there are no file format changes. You might ask, well, why isn't there a 1.8 version of the file format? And we'll come back to that question in a moment, but there is no such thing. In fact, if you follow the links for the file format specification, it currently stands at version 3. So there are versions, I believe there was a version 0, 1, 2, and now there is a version 3. But they are not exactly correlated or tied to library release versions. What we do is something that we call micro-versioning. Each, in a way, object or each construct that we represent in the file format has a micro-version attached to it that gets incremented, and that is actually stored in the file, and that's how the library sort of can make certain decisions. Yes, we constantly update that file format specification, and that's an open published specification, so we don't obscure anything or hide anything from you. The HDF5 file format, I think, is one of the best documented formats. And we come back to that. It has to do with maintaining that forward compatibility feature. That's why basically we do this micro-versioning. But if you ask, well, if somebody gives me an HDF5 file, can you determine or infer from that which library version that HDF5 file was written with? That is not possible. It is not possible, and I can give you some examples, or maybe after my next slide you will sort of see the answer for yourself. But it's basically, there are these different micro versions, but they are not tied to a particular library version. Again, the big question is, why did we choose such an approach? And the reason is basically to achieve forward compatibility. It is sort of what we call the maximum file format compatibility principle. No matter which version of the library you use, by default, meaning unless you instruct the library specifically, the library will write HDF5 files with the earliest version possible. And so, of course, certain features were introduced with certain newer micro versions than micro version 0 or micro version 1. But among those, the HDF5 library will always pick the earliest version possible. The reason for that is, again, if the library, and you can instruct the library to do that, but then that's a conscious and intentional thing on your part. If you were to choose to always use the latest version of the library, and there might be good reasons for that, performance being one, if you make that decision, that has implications that you better understand for the ecosystem around you, for your collaborators, because as we will see in a moment, if you take, for example, version 1.10 and you instruct the library to generate HDF5 files based on the latest version of the file format, then many third-party applications who haven't done the upgrade yet, they will not be able to read these files. However, if you leave the defaults unchanged, then the library will create HDF5 files and sort of primitives and objects in these HDF5 files with the earliest version possible. And that will maximize the chances that a third-party application will be able to read those HDF5 files despite the file having been written by a 1.10 family version of the library. And yeah, as I sort of a short way to summarize that is really this approach assures the best forward compatibility with older versions. Because, yeah, it's very likely in any environment that not all your software, not all your data processing pipeline, not all the components are always sort of in tune with the HDF5 release cycle necessarily. Let's talk about HDF5 forward compatibility, and this is sort of just a summary of what we just said. The forward compatibility, again, extends to two areas, the file format and the library API. As we just said, old versions of the library will read all objects in a file created by a newer library, provided these objects are known to this old version of the library. So let's say, for example, you create a group within 1.10 version of the library, and you did not instruct the library intentionally to use the latest version of the file format. That group will be created in the file in a way that both a 1.8 or 1.6 version of the library will be able to access and read that group. And for the library, what it means that if you have an application written for an API to a in this case, pre-110 API, and you would like to build that application against the 110 version of the library, all you have to do is really, when you compile the file, specify a pre-processing flag. In this case, let's say you have an application that you built against 1.8. If you compile it against the 110 library, you would specify as part of your compilation flags this enable HDF5 v1_8, so the y would be 8 or 1.6. If you build your application against 1.6, but then since we maintain all the older APIs unless they are deprecated in newer versions of the library, that process should be pretty painless and straightforward for you. As far as backward compatibility goes, again, breaking this out into file format and library, definitely newer versions of the library will read all HDF5 file formats that predate that library release, including the current version. We are proud that, for example, the previous sort of family of HDF5 file formats called HDF4, which is still in heavy use today, for example, by NASA. We have no problems whatsoever to read HDF4 files that were written in 1988. Yeah, that's an achievement we are proud of. As far as library APIs are concerned, as long as you do not use any of the new features that are specific in this case to 1.10, your application should just compile and link with the older library without any modifications. Here are some, so this was kind of a whirlwind tour, but if you really would like to get down into great detail, it always helps to, each release of course is accompanied by release notes. Then this general philosophy of backward and forward compatibility is discussed at this URL here. The API changes that happen from release to release and what form they can take on, there's a URL here for that. And then you can always see the current version of the file format and all previous version of the file format at the URL that's listed here for the file format. Now, switching gears, so I think we have a pretty good understanding now that how we do compatibility, how we do versioning. And yes, so HDF5 1.10 brings a lot of new features. There are changes to the file format. There are changes to the APIs. And but with this discussion that we just had about how we do versioning and compatibility and so forth, yeah, it should be clear and manageable for you as users to make that upgrade if there is a need for you to make that upgrade if you would like to take advantage of one of the features that we'll be discussing in a moment. Otherwise, if there isn't really a new feature here, you may wait until there is something that you would like to take advantage of. On the other hand, it may not hurt, even though you do not use any of the new features, just sort of preparing yourself, because one day we will deprecate 1.8, but just preparing yourself for rebuilding your application with the right compatibility flags, just continuing to do what you've been doing successfully. That might be a good thing to do, but so doing the upgrade is not necessarily driven by you are eager to use a new feature. It's just sort of part of a regular maintenance cycle. There is here's a URL that you can visit to get an overview beyond what I will present here today. I've broken out the new features into kind of two categories. One are genuine new features, the SWMR, the single writer, multiple reader access, and the virtual datasets. But then there is another set of features that really deal with performance, usability, and access improvements. And as I stated earlier, the current release in the 1.10 family of releases is HDF5 1.10.1, which we released in late April. And yeah, I hope we can stick with our 6 months maintenance cycle. But obviously, 1.10.2 is not exactly around the corner, but coming soon. So maybe in October, maybe in November, we'll see. Let's start with the first new feature, this single writer, multiple readers feature. And for each of them, I try to break it out into, well, what does it do? What does it buy me? Give me a use case. And what if there are any caveats in using this feature? So as the name says, single writer, multiple readers, this is something to do with you have a process that is writing actively to an HDF5 file, and there's one such process. And then you have reading processes that are accessing the same file in a reading manner. And the interesting thing is, well, you might say, well, I could do that previously. I just had to do some some synchronization, some inter-process communication between these processes to manage that, and that's true indeed. However, the interesting part of this feature is really that there is no inter-process communication required with this SWMR feature. So you can have one process that begins writing, opens an HDF5 file and begins writing to the HDF5 file. And then in a completely asynchronous, uncoordinated fashion, you can have processes coming to that file and opening it and trying to read it. No inter-process communication required. The use case that drove the development of this feature is, of course, let's say you have long-running data acquisition. I mean, nowadays we have experiments and sort of data streams that it takes much more than half an hour. Sometimes they run days or even weeks. And of course, these undertakings tend to be very expensive, and you would like to sort of start analysis immediately, or at least you would like the ability to quickly detect, well, the experiment is going according to plan, or if you notice after 10 minutes that it's not going the way you expected, that an instrument either failed or wasn't calibrated properly, then you want to take action and sort of not incur sort of greater cost and then find out a week later that your 3 days experiment sort of didn't yield very meaningful results. Caveats, many of these caveats are sort of bracketed by currently, and by currently I really mean there is nothing in this feature that would prevent us, in this case, for example, to use SWMR on Windows. The implementation does not use any non-Windows or functions that would not be available in Windows. It's just in this particular example, the case that the testing infrastructure, which requires sort of forking new processes and so forth, is written sort of in a Unixy style. And the reason why we say that there is no Windows support is really that we haven't tested it. In the backs of our minds, we are pretty confident that this will work just fine on Windows. However, we have not tested it, and that's why we tell you it's not supported. Again, you can get the source code, you can build it for Windows and run it, and I'm pretty confident it will work. But again, we told you we haven't tested it. We are not guaranteeing the same way that we guarantee it sort of for Unix-based platforms that it will work. But that might change in the future. So it's really a matter of the customer or the customers who paid for that development. They were primarily interested sort of in more Unix-based platforms. But again, in the development, we didn't do anything that would prevent you from using this on Windows. And once we adapt and augment our testing infrastructures, we may very well test it, and then in the next or in one of the following releases, we might say, yes, we've tested it and we are confident that it will work in your Windows environment. It is also not currently supported in parallel HDF5. And when I say parallel HDF5, I mean the I/O mode of the HDF5 library that uses MPI I/O. Of course, you can use sequential HDF5, the sequential HDF5 library as part of a parallel job that involves MPI otherwise. quite a few people actually do that. But as far as MPI-IO is concerned, at the moment we do not support sort of a collective SWMR write where you would have n tasks in an MPI job that are writing collectively to a shared HDF5 file to do that in SWMR mode. We do not currently support it. Again, it's just a matter of availability and resources and so forth. It might be there in a future release if there's sufficient interest, but currently it is not supported. The next sort of bigger feature is that we call virtual datasets, and the idea is basically, if we go back in HDF 1.8, I forgot exactly which release number, we introduced a feature called external links. So the same way it is very easy on an HTML page to just add a link, to add a URL, to add a link to another page. And we kind of mimicked such a feature in HDF5 in 1.8 where you can create links to other groups, to other objects in the HDF5 file. And people were asking, well, I would like to create a link to an object that resides in a physically different HDF5 file. And that's when we created these so-called external links. And so, which gave you the ability to create sort of interlinked aggregates of files, and the library would transparently handle for you that when it encountered such an external link, it would go out and open the other HDF5 file and then access the object in there, which was very convenient. And virtual datasets, in a way, take that idea to the dataset level, if you wish. The idea is, you may have multiple data sets in the same or different files, but you say, for analysis purposes, to simplify my analysis, my sort of downstream data processing pipeline, I would like these pieces of a data set appear as one large logical data set. And the use case that drove most of that development came sort of from the light source community, where in experiments they have high-speed cameras and detectors, and frequently there is not one detector or one camera that sort of covers the full resolution, the full domain of the data that they acquire, but rather they have sort of multiple cameras or multiple detectors that collectively cover that domain of interest. And the acquisition speeds, the data rates, are very high for these devices in the sort of hundreds of megabytes to gigabytes per second range. And so what they were doing is, and of course, sometimes you have equipment failure, a detector lagging behind, synchronization issues, and so forth. And in that case, what is being done is that the data is actually acquired into separate data sets. But then, of course, for analysis, you would like to recombine them in different ways, in the sense of a spatial decomposition where you have sort of a large domain and you tile it, and then each tile is physically a different data set, but a virtual data set then lets you recombine all these tiles into one large logical data set. Sometimes you also have interleaving patterns in times, and so virtual data sets give you the flexibility to do all that. Caveats, again, currently it is not supported in parallel HDF5, and I'm going to say it once more. When I say parallel HDF5, I mean I/O based on MPI-IO, collective I/O to a single HDF5 file from multiple MPI processes using MPI-IO. Again, if you're running an MPI task and you have multiple tasks using a sequential version of the HDF5 library, writing to separate files, that's not an issue. But when I say parallel HDF5, I mean MPI-IO. So it's not supported there currently. Again, it's just based on demand, we might revisit that in the future and implement it for this type of I/O. And then at the moment, this is more of a usability issue that I just heard will actually be fixed in 1.10.2. At the moment, so we talked about these virtual data sets. You can think of them as aggregates of physical data sets. And when you construct such a virtual data set programmatically, basically you are providing a list of file names and data set names plus sort of a description of the spatial domain that you would like to contribute to a larger virtual data set. The file paths that you specify there at the moment are interpreted by the HDF5 library relative to the executable. And that's, of course, rather limiting. And it was just something that where when we delivered this solution to the customer, it wasn't important to them. But as this feature sort of caught on and many users saw the value in using that feature, they also saw that from a usability perspective, of course, you would like more flexibility interpreted relative to the file, for example, that contains the virtual data set rather than the executable path, or just be more general, have an API call that lets you specify basically a prefix where you can say, okay, for this access, interpret the file paths in this virtual data set relative to this prefix, or have something like an environment variable that's examined by the HDF5 library, and then that prefix is taken from that. So that's coming in 1.10.2, but it's if in the current version, unfortunately, that's a limitation that the paths are interpreted relative to the executable. Another interesting area, and again, this is more for users that are sort of rather proficient in the use of the HDF5 library. It's not exactly for beginners or metadata cache image improvements. What it gives you, or its goal is really whenever you run into performance issues with HDF5, it's very likely that it ultimately comes down to small what we would call small-scale I/O, in the sense of a lot of reads where you just read a few bytes or a few kilobytes, or you write bytes, write small quantities of bytes, and you do this in a random access fashion, so all over the file rather than contiguously or with just monotonically increasing addresses and so forth. And and of course, these small I/O operations in systems where you pay a high latency penalty for what I would call vertical data movement costs. And by vertical data movement, I mean across the memory hierarchy. So starting from disk or your network attached storage into a local disk, into main memory, into sort of through the other tiers of the memory hierarchy. And so what this metadata cache image gives you is basically that, of course, as more experienced users of the HDF5 library, you will know that, of course, the HDF5 library does a lot of caching. It does a lot of caching of metadata, and by metadata I mean information about, for a data set, for example, the types of the elements, the spatial extent, if there's compression, how the data is compressed, and so forth. But it also does caching of, let's say you apply compression and chunking to your data set, then it will cache chunks of data for you. And but as any cache, the caches that the CPU, the hardware maintains, for example, when that cache is cold, so it hasn't really seen any footprint, any activity on your application, early on that cache is cold, as people say, or not very effective. But then once your application has reached a certain steady state, this cache can be very effective because it has all the important data that's accessed frequently, and together it has captured that data. Now, what this feature lets you do is basically persist the state of the cache as kind of an appendix to your file. So there are API calls in the 1.10 API of the HDF5 library where you can instruct the HDF5 library to look for the presence of such a metadata cache image in your HDF5 file, or that let's assume you are starting out with a new file or a file that didn't include any metadata cache images yet. You can instruct the library that on file close, you would like to append such a metadata cache image, so that in the next step of your processing, or when you come back to add additional data to that file, that metadata cache image will be discovered and will be used to sort of pre-populate the cache, and then gives you that advantage that you don't have to start with a cold HDF5 cache, but you can start with a warm cache and get better performance right out of the box. Another feature that, again, is maybe more for advanced users is page aggregation and buffering. And the theme here is similar to metadata cache image is one optimization that may help you in dealing with small random IOs, be it read or write. And page aggregation and buffering is a similar feature where when the HDF5 library, of course, manages the file space, and as the operating system, and in some cases the hardware, does I/O, it doesn't do that sort of in variable length increments, or it typically does that in pages of a certain granularity. And what we did in the HDF5 library is that we took that concept and implemented it at the library level, where when you create a file, you can say, well, I would like to do certain types of metadata or raw I/O in fixed size chunks. And I shouldn't use the term chunks here, I should use the term pages, because chunks are sort of another HDF concept which has nothing to do with this here. But pages, let me call them pages, that's actually the right term here. And so it will do I/O in granularity of these pages, and not only are they fixed size, they are also aligned, because as we all know, in applications, it matters that sometimes at the hardware level, for example, all kinds of exceptions and additional processing needs to take place if an I/O access is not aligned along 8 bytes or 16 byte boundaries, or sometimes even bigger. And so with this feature, you can ensure the size of these pages is fixed and meets your requirements, and B, that these pages are aligned along certain addresses. So if you take any file system, but in particular parallel file systems like Lustre, for example, they are very sensitive to if your I/O, if your reads and writes are aligned with Lustre sort of paging and blocking constraints. And that way, if you want to accelerate metadata and small raw data I/O operations, in particular in parallel file systems, that's where this should be beneficial. Caveats, not well, except one. At the moment, we do not support page aggregation and buffering with the so-called multi or split virtual file drivers. We can, if you have a question there, we can talk about that later, but for many users, most users probably do not use the multi or split VFD, but at the moment this is not supported with those VFDs. Again, currently it's not something that couldn't be fixed, but whenever we develop these things for a customer, it's the customer that drives also what kind of compromises we make in terms of if we support or ensure compatibility with all other features across the board or only a subset. Otherwise, they are intended to be used together, page aggregation and page buffering, so I do not see a use case where you would use one or the other. So this tends to be effective if you use them together. Finally, we made some enhancements to parallel HDF5, and parallel HDF5 again is this scenario where we use under the covers MPI-IO to do collective but also non-collective I/O to a shared file, to a single file in a parallel file system. And what many of our users found is that sometimes they would hit what we then dubbed a read storm or write storm, where a file system like Lustre would be bombarded with many small read requests or write requests. And again, the latency penalty can be pretty drastic in file systems like that. And we have tried to address that by introducing collective metadata operations. So in HDF 1.10, you can instruct the library to do metadata reads. So for example, accessing attributes, for example, but also generally any kind of metadata operations that the HDF5 library might do for you under the covers, to do them in a collective manner. And because for those of you that are familiar already with parallel HDF5, you know that there is a subset of operations in HDF5 that must be performed collectively, like the creation of new objects, creating a new group, create a new data set, and so forth, just to ensure that all MPI tasks in a job have sort of the same global view of the MPI, of the underlying HDF5 file. However, there are other operations where at the moment a lot of them read operations, they can be performed independently, or in fact they are performed independently in the 1.8 family of releases. But now with the collective, with the ability to dictate or suggest to the library to perform these operations using collective I/O, we believe that we have drastically reduced, if not eliminated, a lot of that read and write storm behavior that some of our users have seen in the past. And the use case, one of the main use cases that was driving that, if you take a community convention like CGNS, for example, which is the computational fluid dynamics general notation system, which is a sort of a very popular format or way of organizing your data in the CFD community. They have a lot of metadata, a lot of attributes, groups, and so forth. And what they found is just when you were opening an existing HDF5 file in parallel, or you were creating a new CGNS file, making changes to it in parallel, that these read and write storms, they just yielded a very poor performance, and to the point that it could take on the order of minutes for, let's say, hundreds or let alone thousands of tasks to sort of do I/O against a single CGNS HDF5 file. But then again, all of this is subject to experimentation. So if you have a parallel code and you believe that you are suffering from this problem, and the way to find out if you are suffering from this problem would be to look at a profile of your I/O using a tool like Darshan, for example, or Tau, then it might be worth your while just adding one of these API calls that instructs the library to use collective metadata I/O. That might give you a boost in performance. If it doesn't, then you can talk to us. But you have to dig a little deeper. Then maybe it's not the metadata I/O that is your problem. Maybe there are some other problems, and we are always glad to help and assist. Here is one slide where we earlier talked about versioning and compatibility, and we also provide a set of tools that can help you to make that transition to a newer version easier, and to help you with, okay, I created a file with 1.10, but now let's say there is a metadata cache image in there. MATLAB doesn't know yet anything about metadata cache images. Does that mean I can't now use MATLAB to access that file, and so forth? So here are some tools, here are some tools that may help you with sort of bridging these potential incompatibilities. So let's start at the top. Let's say, and this is the C API call here, that you can use to instruct the library to not use the earliest version of the file format to create objects, but rather to use the sort of the hottest and newest and latest. You can use the H5P set libver bounds call to tell the library, hey, use the latest and greatest, and maybe later you regret that. But let's say you would like to go back to 1.8. Well, the good news is you can go back to 1.8. The downside, however, is that all data, and that's why this is in bold here, all data in the file has to be repacked for that. And by all data, we mean the metadata and the raw data. So if your file is 3 terabytes, then unfortunately, that entire 3 terabytes needs to be rewritten, will be touched and rewritten. But that's in a way the price you pay here for asking for the bleeding edge file format and then wanting to go back to 1.8. Things are a little less data intensive, if you wish, for some of the other situations. So let's say, for example, that SWMR feature is really attractive to you, where you say, hey, I have a long-running data acquisition and I would like to start reading from that file early on, and that's really a great feature I would like to use, but I have 1.8 infrastructure to analyze the data and so forth. Well, the good news is that we provide 2 tools that can help you here. One is this tool called H5 format convert that basically removes some SWMR specific information from that file. And the good news, this is just metadata. So in that case, this is an operation that's extremely fast, takes less than a second, where we basically strip out some of that metadata, and assuming you are not using any non-1.8 incompatible features, your raw data will not get touched, it will not be changed in any shape or form. So this is very fast. The other one is you can again use H5 repack, and so it's your choice really at this point, but the net effect in both cases would be the same. I'm going to speak. I didn't speak about partial edge chunks. We can talk about that offline, or if you have more questions, I can point you to the documentation for that. I'm not going to talk about it here. VDS, virtual dataset. Again, virtual datasets are not available or unknown to 1.8 versions of the library. And again, H5 repack is your tool if you would like to in a way, materialize a virtual data set into a physical data set in a new file that is then 1.8 or 1.6 compatible, you would use the H5 repack flag. You would use the H5 repack tool with the -L layout flag, and then you have options for L. Because for the layout, for example, you may choose to create a large contiguous data set that basically brings together all these component data set in one large physical data set, or you might opt to include compression and sort of with layout you would provide the chunking that you would like to see and then the compression method to apply. So H5 repack again is your choice here. And then last but not least, we talked about the metadata cache image. So let's assume in your acquisition cycle, you benefit greatly from metadata cache images, but then you would like to pass that file on to analysis into a pipeline that does not understand metadata cache images. Well, in this case, it's very easy. We have a tool called H5 Clear that can basically strip out that metadata cache image, so it will not create any problems, any issues, any incompatibilities in your downstream pipeline. And it's very fast because it does not touch any raw data. It just, again, strips out that metadata cache image. Is very non-intrusive, very fast, and helps you there. So I think there is a table like this online available, and you can see references from the URLs that I listed here. So our homepage, hdfgroup.org, shouldn't be a surprise. The release-specific information for the 1.8 family of releases can be found at the URL listed here. Likewise for 1.10. I mentioned already the new features overview, and then we have these RFCs, these design documents that describe in very great detail all these different features. And then finally, sort of the programmer's best friend is certainly the API specification, which has all the functions, the C bindings, the Fortran bindings, and then references also to Java and some of the other APIs. And I believe that's it. If we have questions, or if we have time for questions, I'd be happy to answer questions.
Microphone. So we had one question from a viewer asking, will HDF5 benefit from burn buffers?
He probably means burst buffers. Well, absolutely, because I have used. It would be interesting to hear the specifics. I personally have used burst buffers in a very simple fashion. Earlier, I mentioned this issue, of course, of high latency. So let's say you work at sort of one of the large supercomputers, and your HDF files are stored in Lustre, and let's say your I/O pattern is such that you have a lot of small metadata operations or even small raw data operations, then the performance penalty, since the latency going over the network, nowadays the craze and these big supercomputers, they don't have local disks anymore. That's pretty much the niche that to some degree burst buffers will fill. And so what you would do is, and I've done that myself with great success, is let's say on a Cray system, there is typically, when you submit your job, the burst buffers, for example, on systems like Cori, they support the, I forgot what they call that feature, the stage in and stage out. So declaratively, in your job submission, in your batch script, you can specify the amount of burst buffer you would like to reserve, and you can point it, for example, at a directory where the input HDF5 files, let's say, reside, and then the scheduler will make sure that before your job begins, that the data is sort of paged in or staged in and available when your application runs. That and yeah, you do not pay the loss of performance, the latency penalty, the vertical I/O penalty, so to speak. And I've used that with great success. And the same goes for writing. So writing to the burst buffer, even if that write includes some frequent, smaller, random I/O, since burst buffer, the burst buffer is so much closer, topologically speaking, to the compute nodes than the lost of file system. That will give you better performance. And then likewise on the way out, you can use that, I believe they call that in the scheduler, it's the stage out feature, where you can then designate sort of a directory or a file system where you want the data then to be moved once your job is complete. And so yeah, definitely burst buffers help, and no changes if you use it just at that level with the sort of stage in and stage out. You do not have to change anything in your application. So in that sense, the HDF part is completely agnostic to the presence of burst buffers. But if you would like to take programmatic control of the burst buffer management, then there might be, I know there is a library that might be slightly different from center to center and from system to system, where you can sort of programmatically control the allocation of burst buffer space and so forth. The one thing that I will mention is with HDF5 110 is that you have to disable file locking. There is an environment variable, and if you give us your email address, I'm happy to send you an email with the instruction. What I found is when I used burst buffers with HDF 110, I had to disable file locking, which is sort of, if you read the design documents on 110, this is how we control some of the SWMR properties. And if file locking is available on a file system, we actually use it. If it's not available, we don't use it. But if it's available, then you can force it to be disabled. And there's an environment variable for that. And I remember, I had to set that environment variable to correctly, to make sure that my job worked correctly with the burst buffers.
So our viewer confirmed they meant to say burst.
Oh, yeah. Okay.
So that's good. Mm-hmm. Another question from a viewer. Are there any plans to provide bindings for other languages?
Well, I would give a two-part answer to that. At a high level, yes. What we have seen is, well, first of all, there is a large pool of bindings available. It would be interesting to hear which particular language the questioner has in mind. What we like to see, and I would point to, for example, Python. I mean, of course, our main focus is really HDF5 and the library, and we certainly, if there is somebody out there who would like to write language bindings for a particular language or a particular environment, we would support them to any extent, in any shape or form we can do that. If there is something where they say, with this particular language or this environment, this is really a thorn in my side, what can we do about that? How can we mediate that? By all means, let's have a discussion. But what we have seen is, I think there is relatively little appetite on our end, the HDF group, to create new language bindings, because the main difficulty for us is we are not the experts in that language, and as the questioner I'm sure knows himself, there's a difference between sort of writing programs in a language that you've just learned and writing programs that are really, I would say, idiomatic in that language. I mean, you can write a Python program that looks like a C program in Python, but more experienced Python programmers would look at this and sort of shake their head or roll their eyes. And so that's why we prefer that if there is somebody that is fluent and versed in a language and they would like to create bindings for HDF5 in that language, we would like to support them to any extent possible, because then that gives us a certain assurance that hopefully by programmers in that community, by users in that community, they will recognize this as that is their language that they like, and HDF sort of fits in and blends in sort of with the idioms of the language. And again, I would point to H5Py, the Python module for HDF5, where that has been very successful, where Andrew Collette has created these high-level bindings that really look like Python and feel like Python. And then under the covers, there are low-level bindings that experienced Python programmers will fall back onto only if they need control that is otherwise only available at the C level. Or but most, I mean, I'd say 80 to 90% plus of modern Python code that deals with HDF5 is completely written in the high-level APIs, and only in very extreme cases do people resort to that low-level API that is available. So the answer is we are interested to support HDF5 in as many languages as possible, but we are always looking for that collaboration, for that partnership, because we understand something about HDF5, but as far as new languages are concerned, we don't really have the confidence that we would do a good job in sort of, first of all, specifying such an interface and then maintaining it in the long term. I mean, as probably many people in this discussion listening in know, that it's really the maintenance, the longevity that really is 80% plus of the effort. I mean, throwing something out there, and to our own dismay, we have seen things produced by the HDF group in terms of language bindings and so forth that have not stood the test of time. And I think it's at least served us as a lesson to say, well, we'd rather team up with someone who knows these things inside out, who is an expert there, and then we'll support them, but they will create something that will stand the test of time.
So the viewer was curious about Swift.
I personally do not know, and so I'm just sort of illustrating my own point here. Yeah, I believe I've seen bindings there for Swift, so obviously everybody can do a Google search. And but again, it's really this: is this something that an intern did? And what we see frequently, and in some cases did ourselves, is if there was a customer or a project where somebody said, well, we just need HDF5 bindings, we don't need the complete API, we just need a subset of features like opening, creating files, opening, creating data sets, creating groups, but that's it. We are not interested in compound types, just scalar types, ints, floats, strings. That's good enough for us. Done. And it's probably true for most languages that if that's your goal, well, creating that language, these language bindings, let's call it that, is pretty straightforward. But unfortunately, it is also setting yourself up in most cases for this being short-lived and then not really being taken up, because that then requires really a community coming together around those bindings and then taking them forward. And again, if this particular individual, if you have an interest, send us an email. And if you have questions, how we can, or sort of thoughts about how we can assist and help you in taking that forward, by all means.
Okay. There are no other questions from the viewers. I would just ask a general question that we always ask if someone wants. The presentation is probably very good for people that already know HDF. If they want to learn HDF, where do you recommend they go?
Well, definitely to our website, but then I think on YouTube there are great resources available if you just search for HDF5 on YouTube. There are plenty of videos. So we do a lot of tutorials at supercomputing, at many of the workshops that the DOE, for example, puts on. Many of them are focused on high-performance computing, parallel I/O, and so forth, but there are also some general introductions. I think that's great material. And then, of course, Python being sort of a very dominant player in that space as a language with also very advanced bindings and very stable bindings. If you go to, for example, one of the Python distributions by Enthought, they have great training material on HDF5 and Python. But then also, if you look at the SciPy, the PyCon type conferences, there's typically at least one, more often 3-4 different presentations that are application specific, but people use HDF5 and they show how they used it. And then, picking up a tool like PyTables or Pandas, you don't have to necessarily always go sort of to the HDF level, because most of the time there's a problem that you want to solve, and going back all the way to HDF5 is maybe not that helpful. Just look for Pandas, PyTables, one of the tools that sort of give you a lot on top of HDF5. They give you the performance benefits and so forth, but they also give you things like data frames and tables and sort of abstractions that just make everyday life easier and sort of more suited for the kinds of analysis that you would like to do.
Great. Well, join me in thanking Gerd for a tremendous presentation today. Very useful, I think, for people that are already using HDF, and some good insights for people that want to get started. So thank you. Next webinar is coming up, Eclipse by Robert Smith, next week, August 16th. And then it's September 20th, Justin Wozniak will be talking about Swift-T. We'll be sending you links to the final edited version of the video for this session, which you'll be able to access on YouTube. And we ask all of you to share your thoughts and perspectives for how we can continue to improve through a short survey that we'll be sending to you. With that, we thank you and hope to see you in the next webinar session.